Once an object starts spinning, rotating or revolving, then it's moving. And so we can also describe rotational energy of a system, which of course would just be the kinetic rotational energy of a system. Right? And so first is to start with our fact that we know that the kinetic energy of an individual particle is equal to 1/2 mv squared, right? That's for one particle. But if I have a circular object, then there are multiple particles all over the place. And when this object starts to rotate, they all rotate at various speeds based on their particular radii away from the center of the circle. And so a rotating object would have, for the rotational kinetic energy, we would have Ke being the sum of the change in kinetic energy of all 1/2 mv squareds, right? And so if we utilize the summation here and the fact that we know that as a rotating body we can substitute V being equal to omega times R, then this kinetic energy formula turns into the summation of 1/2 times m times r squared times omega squared, where I've substituted in omega times r for v. I've written it in this particular format because we see that the summation of mr squared, again, is something that we've already recognized. We know that I, the moment of inertia for a rotating body, is defined as the summation of mr squared for all particles rotating. So the kinetic energy of a rotating body is truly 1/2 I omega squared. And this formula should look very similar to our original formula, right? It has a inertia characteristic along with a motion characteristic squared times 1/2. So the rotational kinetic energy is equal to 1/2 I omega squared. So when we talk about taking an object like a ball and putting it on top of an incline, as the ball rolls down the hill, if this object is anything other than a point mass, then it has a distribution of particles over its radius. And so now we have to describe this thing as rolling as a function of the incline, but also of its rotational inertia characteristics. That's all to say that the total kinetic energy would be the kinetic energy based on this velocity that's increasing as it rolls down the hill, but also the omega velocity that's rotating, that's causing it to spin faster and faster and faster as it goes along. And so this would be its kinetic energy linear plus its kinetic energy rotational. And so the total kinetic energy for a rotating system, or excuse me, the total kinetic energy for a rolling, moving, rotating object. So in other words, a round object that has a radius and a distribution of particles that is now moving laterally while also spinning, truly has a kinetic energy total of 1/2 mv squared plus 1/2 I omega squared. In this case, the V is the linear or translational motion, and omega is the rotational motion. Keeping that in mind, we can also think about the fact then that a form of energy that causes it to transition from potential to kinetic or others is rotational work. Rotational work would be based on a linear analysis where work is equal to force times displacement. But we know that in a rotating body, right, if I had an object here and this was the center of the circle and I go to rotate it around like this, right, it moves through an arc length L based on an angle theta from here to there over a horizontal radius of r by applying a force tangential to the path here as F, right, that causes this to rotate from this position to this position. That force is really a torque in a rotational body, right? And so what we're seeing is that this D can be described as the change in L from here to there, or just L from there to there. And what we've seen is that L is a function of theta, and so we know that work then could be F times the change in L in this particular case. And the change in L is the same as saying the radius times the change in theta. And what we see is that force times radius is our old friend torque. So rotational work, as expected, is a torque applied through an angle as opposed to a force applied through a distance for a linear relationship. And so we've got two ways to describe energy of a rotating system. It's applied force through an angle displacement, or it's total energy based on its linear motion and its rotational motion. And of course, if it doesn't move laterally and only spins, right, if it was just fixed on an axis and spinning, then its energy would be solely rotational energy as 1/2 I omega squared.